Thanks for the introduction. It's my great honor to receive this Larry Brown Award. I'd like to thank the committee and thank my collaborator Minerva Mukhopadhyay from Indian Institute of Technology and my advisor David Johnson, and thank you all for coming. Today I'm going to talk about learning and exploiting low-dimensional structure in high-dimensional data. So the main focus of my talk is about manifold learning, where we propose a new dictionary called the Spherits as a nonlinear local dictionary to learn the manifold. And then we propose the so-called spherical PCA as a spherical analog of PCA to locally fit the manifold by a sphere. And motivated by the idea of sphereless, I will talk about multiple applications, including density estimation, classification, and geodesic distance estimation. It's very common to collect complex high-dimensional data. And in some settings, we have a limited sample size. We don't just want a black box for prediction. We want to learn what is happening inside the box. So that means we want to learn and interpret low-dimensional structure and relation in the data. So we need some sort of dimension reduction, which is a very popular area, I believe. So suppose for simplicity, we have some IID samples xi living in high-dimensional Euclidean space R to the p, where this p is the dimension of the ambient space, which can be large. The dimension reduction method can be based on the model xi is equal to f of eta I plus epsilon I, where this eta I is called the latent factors living in a low-dimensional space. Here we assume the intrinsic dimension is small d, which is much smaller than p, the ambient space. And this f is some unknown function we want to learn, and epsilon I is the measurement error. We always assume this epsilon I follows a, for example, Gaussian distribution with zero mean. If f is linear, then we have some well-established factor analysis and PCA tools. But in most real data sets, this f is highly nonlinear. And there are multiple approaches when f is nonlinear. For example, approach one is that we can use a locally linear approximation. For example, we can cluster the data into a lot of local pieces, and we see within each local neighborhood, we can apply linear method like PCA. The motivation of this kind of approach is that a manifold can be approximated by tangent space locally. And this linear method is just to help you to find the best tangent space. And the other approach is nonlinear factor model. Assume this latent factor eta I follows some standard Gaussian distribution, and then we want to learn this f. Approach two includes Gaussian process latent variable models and variational autoencoders. But they are complex black boxes, not identifiable or interpretable. Our goal for today is to develop a simpler approach, including nonlinear alternative to PCA, we call it spherical PCA, and some model-based method to do statistical inference. So in order to develop some method, we need some assumption. Here we assume the data xi are concentrated near some Riemannian manifold M with intrinsic dimension small d, much smaller than p. So manifold learning algorithms seek to exploit the manifold structure in some mapping from xi to eta I living in the low-dimensional space, preserving certain structure. For example, if this eta I preserves the pairwise distance matrix, then this algorithm is called the isomap. Or if we want to preserve some local, like a quadratic form, then this is the Hessian local linear embedding. And similarly, we have some other algorithms in this class, like Laplace eigenmap, diffusion map, t-SNE, etc. The misnomer is that the manifold estimate M hat is not produced by these algorithms. Actually, the output of these algorithms are just the latent factors eta I, but we don't know what does the manifold look like. For example, in this two example, it's a Swiss roll. If you run this algorithm, you will see some two-dimensional embedding or two-dimensional coordinates in the latent space, but you cannot see the spiral in R3 or in higher dimensional ambient space. But in some settings, as we will see later in this talk, we do need these manifold estimates M hat. To learn this M hat, we need some dictionary. Dictionaries are made up of simple pieces used in approximating X. And almost always these local patches are linear. For example, this kind of state-of-art algorithm called the geometric multi-resolution analysis. And this is a locally linear method. The idea is as follows. So first we split the space into a lot of local pieces, and in each local piece we'll apply PCA. And they have a fancy partitioning algorithm depending on the geometric wavelets. And so this simple locally linear method are conceptually easy, and computationally it's also efficient. But the only problem is that if the manifold has very large curvature, we need too many number of pieces or local bases to approximate the manifold. While, for example, here is a single circle. If the curvature of the circle is very large or the radius is very small, we need many pieces. In this figure, we need 17 tangent lines representing or approximating the manifold. So the most natural generalization is to consider a second order approximation, because linear method is just first order approximation. A second order approximation can be represented by this quadratic function x transpose hx plus f transpose x plus b is equal to 0, where this h is a p by p symmetric matrix, f is a p by 1 vector, and b is a scalar. Or you can consider some higher order approximation like degree k polynomial. This is the generalized PCA. Or you can consider even more flexible local basis, the principal curves. But the problem for this kind of generalization is that the number of unknown parameter will be of order p to the k for a degree k polynomial. Even for the quadratic case, it's still of order p square. And as I mentioned, sometimes this p is really huge. So we don't want to treat one problem for another. We don't want these many parameters. We want something in between. We tend to call it a 1.5 order approximation. So let's look at where does this p square come from? It comes from this h. So if we can make this h a special case, then we can decrease this number of unknown parameter from p squared to p. For example, we can make this h to be identity. That's the simplest quadratic form in some sense. Then this equation will have only p plus 1 unknown parameter of order p. And this is from the algebraic perspective. If we think about this geometrically, this corresponds to the constant curvature space, because first order approximation, that means we use tangent space with zero curvature. It's just flat Euclidean space. So here we can consider a constant curvature space with non-zero curvature. This corresponds to the equation of a sphere. We can rewrite if h is identity, we can rewrite this equation as the distance between x and c is constant r squared, where this c is the center of the radius. It's the center of the sphere, and r is the radius of the sphere. Okay, here's one figure. This p is a tangent line at point. This is the tangent line at point p of this curve c. And this is the oscillating circle, which is the unique circle that is tangent to the curve at P with the curvature the same as the curvature of the curve. And you can tell that this oscillating circle approximates the manifold much better than the tangent line. So as a result, we propose to use pieces of spheres, or we call it spherelets, as a new dictionary. So often there are fewer spheres than hyperplanes to obtain the same approximation error. Each sphere has few parameters and simple geometric objects, so it's very easy to feed the data by some sphere. I will talk about the algorithms later. Before that, let's look at the approximation power. Assume M is a compact third differentiable d-dimensional Riemannian manifold embedded in Rp. We want to bound the number of pieces needed to obtain the approximation error epsilon. Notation is H epsilon m is the minimum number of hyperplanes. H means hyperplane. Epsilon is approximation error. M is a manifold. Similarly, an S epsilon m is the minimum number of spheres. This S means spheres. We want to find the upper bound of these two quantities. Let C1 and C2 be two constant depending on the geometry of M only, and alpha epsilon is some weight between 0 and 1 depending on both M and epsilon. So we show that the minimum number of hyperplanes is upper bounded by epsilon to negative d over 2 up to a constant. Similarly, this minimum number of spheres is bounded by a linear combination of two terms. The first term is similar to the hyperplane case, multiplied by 1 minus alpha epsilon. And the second term is actually our gain. It's epsilon to negative d over 3. This is a better rate, but multiplied by this alpha epsilon. Two extreme cases are as follows. When alpha epsilon is 1, then the first term disappears, and the order decreases from negative d over 2 to negative d over 3. Another extreme case is when alpha epsilon is 0, then they have the same upper bound. And so that means we can do at least the same as the hyperplane case, depending on the geometry or this alpha. And so this epsilon to the negative d over 2 shows the curse of dimensionality because epsilon is very small. Even if we know how to perfectly choose the pieces, we still need a lot of pieces as d increases for small epsilon. But sphereless can decrease the impact of the curse from negative d over 2 to negative d over 3 if the manifold is nice enough, or equivalent to say this alpha epsilon is large enough. And the geometric interpretation of alpha epsilon is that if there are many good points, I mean the changes of in the principal curvature is small, then we call it good point, then this alpha epsilon will be close to 1. So I will skip the technical detail, but here's a figure showing how local sphereless works. So here's the underlying manifold, a Euler spiral. We can approximate it by a bunch of tangent lines represented by this line in different colors. Each color represents one local piece. Or instead, you can approximate this curve by a bunch of circles, or part of the circle, of course. And you can see that there are fewer number of pieces or fewer colors than this local PCA. And so in addition, if you look at the intersecting part, the local sphereless has the approximation from local sphereless is smoother than the local linear method. Okay, then the problem is how to find this best circle. So to do this local PCA, we all know how to solve this. For each local region, you just collect the sample coherence matrix and you do the eigen decomposition. You collect the first d eigenvectors, and that's the best hyperplane to approximate this local region. You don't need to solve any like gradient descent algorithm. What about SPCA or sphereless case? And the good news is that we can do a similar optimization. So we still have a closed form solution for this sphere. We don't need to do gradient descent. Okay, we call this spherical principal component analysis because it's a spherical analog of PCA. We call it SPCA. So given some data X, you can always find the best center C hat and the radius R hat of the best sphere in closed form. There is no gradient descent at all. So we call this projection to the best d-dimensional sphere the D spherical projection. This is similar to the PCA linear projection. And again, they are like simple analytic forms and can be trivially used in place of PCA in many settings, as we will see later in this talk. So the main theorem suggests that we should see big gain in practical performance. We initially developed some simple local sphereless algorithm and compared to local PCA and GMRA. Here's the two examples I mentioned, the Swiss roll. So the X coordinate is the log of number of partitions or local pieces, and the Y coordinate is the log of mean square error. So the lower the better. The blue one is from our local SPCA, and the red one is from local PCA. This reason is due to the overfitting. And the green and yellow curves are from the GMRA. You can also see some results in real data, but I will not present them here. So spherelids provide a useful alternative to PCA that incorporates non-zero curvature. Motivated by the spherelids, we want to develop some model-based approaches like for density estimation on remaining manifold. Here are two motivating examples. So if we have some data like this, so the support of the unknown density is some remaining manifold with non-zero curvature. We have some existing method to do density estimation, but we are not sure about the performance of these algorithms. So are they good enough for this case? Unfortunately not. So approach one is a nonlinear factor, latent factor model like GPLVM or variational encoder. Approach two is frequentist kernel density estimation. Approach three is kernel mixer model, where this K denotes the kernel and pi h is the weight of the H component, theta h is the parameter for the H component. This summation can be finite or infinite depending on how you mix this kernel. Approach one doesn't give us an expression for of the estimated density f hat, so we rule it out. Okay, let's look at the performance of 2 and 3. Here's the observation. We have this observed data. And we want to learn the density from these observations, and then we want to further generate new samples from the estimated density. We call it predictive samples. So the second panel is the predictive samples from kernel density estimation with kernel chosen to be Gaussian kernel. So we expect the predictive samples to be similar to the true samples. And the third panel is from the kernel mixer model. Again, the kernel is chosen to be a Gaussian distribution, which is very popular in practice. And the last panel is from our method. I will talk about details in a minute. So you can see that for this Gaussian kernel method, no matter you choose a kernel density estimation or kernel mixer model, you cannot see the true underlying geometry. And it's a similar story for the Olympic rings. You can see you can see 5 clear rings from our algorithm, but kernel mixer model completely fails. Kernel density estimator kind of works in some sense. You can barely see the 5 circles. So the sample size is not that small, and we are using some current very popular packages for bandwidth tuning, but still they don't work well. We expect the dirichlet process mixture to do better, but actually it's doing worse. By the way, this is a DP mixture of Gaussian. It's an infinite number of components actually, but still it doesn't work. So why they don't work? Because it's essentially because the kernel is bad. It's not because of the kernel mixer model or this kernel density estimation, it's because of the bad kernel. Essentially, this Gaussian kernel is supported by a Euclidean space, which is flat. So that means you want to approximate the support or the underlying manifold by a bunch of linear spaces or tangent lines. Okay, so as we have seen that when the manifold has large curvature, we need too many components to approximate the manifold while. Then if you want to estimate the density, you still need a lot of components or local kernels to approximate the density while. So this exactly is our motivation for spherelids. So we have seen that we can approximate the manifold better by a bunch of spheres than hyperplanes. So in terms of density estimation, it's reasonable to believe that if we can find some curved kernel, and the mixture of that kernel will be better than the mixture of Gaussian kernel, because spherelids have a better approximation power. So then we need a new kernel or probability distribution that accommodates non-zero curvature. There are some existing literature on defining new multivariate kernels, but mostly people focus on skewness or heavy tail property. So there is little literature in defining kernels with non-zero curvature. So we need to invent one appropriate kernel here. The idea is very simple and inspired by spherelids. We want to define some distribution that is supported near some sphere. And by controlling the curvature of the sphere, we can control the curvature of the kernel. Here's the definition. First, we generate a random variable z from some von Mises Fisher distribution, which is supported on the unit sphere centered at 0 or origin with radius 1. This von Mises Fisher distribution has a location parameter mu and the scale parameter tau. This basically is a precision. And the density function is proportional to the exponential of tau times z transpose mu. And the normalizing constant is a little bit more complicated than the Gaussian distribution. Okay, and then we do a affine transformation. Let y be r times z plus c. Because d lies in the unit sphere, then this y will lie on a sphere centered at c with radius r. And then we add a measurement error epsilon, which follows a standard Gaussian distribution, maybe not standard, but zero mean with a diagonal coherence. So this resulting random variable x will have the full support in the entire space. But because it comes from a sphere centered at c with radius r plus a noise, then we can believe that this x will focus or concentrate around this sphere. So we call this the resulting distribution of x the Fisher-Gaussian distribution because it's essentially a convolution between this von Mises Fisher and this Gaussian noise. Unfortunately, we do have a closed form solution for the density function of this Fisher-Gaussian density. There we have 5 parameters. C is the center of the sphere, R is the radius of the sphere, mu is the location parameter, tau is a scale parameter, and sigma square controls the noise. So C and R basically control the geometry of the support, and these 3 parameters controls the kind of the location and the precision, etc. And we have a normalizing constant here, which depends on the modified Bessel function of the first kind. This is not surprising because if you integrate something on the unit sphere, you will get this modified Bessel function. So let's look at what does this kernel look like. Here's one example of this Fisher-Gaussian kernel. You can see it's basically concentrated along this part of the circle. So this is a circle, but you can look at the scale of x and y coordinates. They're not in the same scale, but believe me, it's a circle. It's a part of a circle. Here's another example, and you can compare the different parameters. The first parameter is the center, so it's hard to tell from the figure. But if you look at the coordinates or the scale, you'll see the difference in the center, and the radius is the same. And the third one is mu, the location parameter. This is in this direction, and this -1 over square root of 2 represent this direction. And this tau is 1 here, and tau is 2 here. This tau is the scale parameter in von Mises Fisher. You can tell that so the smaller tau, the more spread within each circle. If this tau goes to infinity, then it will degenerate to a direct measure at this location parameter mu. But in the other direction, if tau goes to 0, then it will degenerate to uniform distribution on the entire circle. And this sigma square basically controls the deviation outside of the sphere. The larger sigma square, the wider of the kernel. So the second one has a larger sigma square because this is a measurement error. Okay, let's look at the mixture of this Fisher-Gaussian kernel. Here is a mixture of 5 kernels, and the radius is always 1 for these 5 kernels, but we are changing the mu, tau, and sigma square, of course, on C. Then we can, as I said, we can control the curvature of the kernel by controlling the radius of the sphere. So what if we vary this radius across kernels? Then we will have a much more flexible representation of the mixture. Here's my favorite example. We call it the Fisher-Gaussian snake. You can see 5 kernels, 1, 2, 3, 4, 5. And the curvature is changing across this curve because the radius is changing. So the point of the last Fisher-Gaussian snake is that this Fisher-Gaussian kernel is much more flexible than Gaussian distribution. You can imagine that if the true density is like this, and you want to approximate this true density by a bunch of Gaussian kernels, how many components you need to get a good approximation error. At least it's much larger than 5, right? Okay, so we implement Fisher-Gaussian mixtures in a Bayesian analysis because I'm from Duke. And so we use a two-layer formulation to allow multiple von Mises-Fisher components on each sphere. So the first layer is the mixture of spheres, where we use a Dirichlet process. We allow infinitely number of spheres. So that means we want to learn the manifold by a bunch of spheres, and with each sphere, we want to learn the density in that sphere, where we use the second layer, the mixture of kernel. And in that layer, we use a finite mixture because we know sphere is very simple, it's compact, so we don't need an infinite number of components with each sphere. And we show the large support property and the posterior consistency of this DP mixture of Fisher-Gaussian kernels. And fortunately, we do have some nice conditionally conjugate pairs for all parameters except the tau parameter, the scale parameter of the Mises-Fisher, where we need a one Metropolis-Hastings step. So others, we do have this Gibbs sampler, which is very simple. Let's look at how it works in practice. Here's another two example, the torus. It's a two-dimensional surface embedded in three-dimensional space. And again, the first panel is observation, and second one is the predictive samples from the kernel density estimator, where the kernel is chosen to be Gaussian. And the third one is the DP mixture of Gaussian. And the last one is the DP mixture of Fisher-Gaussian. You can see only by Fisher-Gaussian, you can see the hole in the middle. For others, because essentially the Gaussian distribution is supported by the entire space R3, you cannot see the hole in the middle. And similarly, you can also try to label data set. For example, we have two classes of data, and then we can separately estimate the density of two classes, and you can generate new samples. You can see that only DP mixture of Fisher-Gaussian can recover this low-dimensional geometric structure. And we also have some real data examples, like this balanced scale data from some psychological experiments, where we test the sum of log likelihood. You can see that it's the same order as this observation. So the best one is DP mixture of Fisher-Gaussian, and the second one is the kernel density estimator with Gaussian kernel, and the worst one is DP mixture of Gaussian. So it's the same order: DP mixture of Fisher-Gaussian, kernel density estimation with Gaussian, and DP mixture of Gaussian. Okay, so inspired by spheres, Fisher-Gaussian distribution gave out a alternative to Gaussian kernel, and it can be used for multivariate modeling and in other settings. In the remainder, I will discuss two more applications also inspired by spheres for classification and geodesic distance estimation. So given labeled data, xi, yi, where this y is the label in class 1 to L, this xi is in high-dimensional space Rp. And there's a huge literature on classifier, but methods struggle when the feature distributions have nonlinear intersecting and entangled support, for example, in this second panel. The first one is linearly separable, so it's very simple. But the second one, so each color represents each class. You can see that the support of the three classes are intersecting with each other. A neural network can potentially deal with this if the sample size is good enough, or I mean large enough. But if the sample size is limited in some scientific settings, it's really hard to classify this kind of data. So motivated by these two examples, we propose this called the local manifold approximation classification. We call the LOMA. So assume points with label J are close to manifold Mj. So that means, so the points with label 1 is close to this red manifold. The point with label 2 is close to this blue manifold, etc. So it's very reasonable to assign this X to the class J having the smallest distance between the point and the manifold Mj. Then the problem is Mj is usually unknown, but we can approximate this Mj. this is another example that we need the estimate of the manifold mj hat instead of just getting the latent vector eta I. So then if we have the manifold estimate mj hat, we can assign x to the class with the smallest distance between x and mj hat. And this distance between a point and the manifold only depends on the local estimation of this mj, because the distance only depends on x and the closest point on mj hat. Here's a figure showing how Loma works. The green dot is the point to be classified. And this M1 hat in red is the local estimation of manifold 1, this curve. And this M2 is the local estimation of the second manifold, M2 hat. And the distance between this point and M1 only depends on this local approximation. The manifold far away from this green dot doesn't matter actually. So this means we don't need to learn the manifold globally, we just need to learn the manifold locally. That's why we call it the local manifold approximation classifier. Then how to learn the manifold MJ hat? Again, there are a bunch of manifold learning algorithms. So you can use any manifold learning algorithm here in this Loma framework, but as said, we have already seen that we can approximate a manifold by a sphere locally, which has a better performance than the hyperplanes. So here we use sphere to locally learn the manifold. And sphere is also very convenient computationally, and we have this SPCA, and it has much better performance than the linear method. And again, the distance, so the distance between a point and a sphere has a closed form, like the linear projection from X to a hyperplane. So we have a spherical projection from X to some sphere that has a closed form solution. So we refer to the simple algorithm as the SPA, spherical approximation classifier, we call it SPA. So SPA is a very special case of Loma, but feel free to replace this spherical approximation by any other approximation. You will get the corresponding version, but still it's in the Loma framework. Okay, here's the result for the funky curves. I mean the three curves intersecting with each other. So the best one is SPA. The y coordinate is the classification accuracy, and the x coordinate is the training sample size. You can see the deep neural network. At first, when the sample size is only 150, it struggles here, but as the sample size increases, it started to catch up with other algorithms like decision trees or k-nearest neighbor or support vector machine. And it's reasonable to believe that if the sample size is even larger, then this deep neural network will beat any other algorithms. And so we want to learn the asymptotic behavior of this SPA classifier. We assume the data are noisy due to some measurement error. So mathematically, we assume this xi is equal to zi plus epsilon I, where this epsilon I is the measurement error with zero mean and a diagonal covariance. Then we assume this Zi follows some unknown density rho, and the support of rho is a union of two manifold, or more manifold depending on how many classes you are classifying. So we assume this Zi is from some manifold M with label Yi. This is the standard setting, but here we don't know Zi, but we observe Xi instead. Let Y be the true label and Yn hat be the predictive label given by SPA, where this N means the sample size. We want to learn the asymptotic behavior of misclassification probability as N goes to infinity. So we show that asymptotically, the probability that we misclassify this Y is upper bounded by this complicated formula. I do want to mention a special case is that when the noise level sigma square goes to 0, which means there's no noise, then this upper bound degenerates to the measure of M1 intersecting M2. This is not surprising because if a point is in the intersection of two manifolds, basically it's impossible to classify it correctly. And if the noise level is non-zero, we have this complicated upper bound. And for image data, we know P is really large, so we need more samples to have a good performance. For example, the convolutional neural network works for image data, but it works when N is large enough. And SPA does better when the sample size is not that large. For these USPS handwritten digits, the dimension of each figure is, for each image is 255 because it's a 16 by 16 pixel. And so here we can see that as the sample size is very small, convolutional neural network is not that good, but it start to catch up with other algorithms. So here I want to mention when the sample size is only 1,000 and there are 10 classes altogether representing figure from 0 to 9. So in each class, the sample size is actually 100, but the dimension is more than 200. This is a P greater than N framework, but still SPA works because we assume the manifold has a much smaller intrinsic dimension. So in this example, I believe the intrinsic dimension is 8 or so. So it's much smaller than 256. That's why it works when the sample size is small. Okay, I want to change to the last topic, from labeled data to unlabeled data. So that means we switch from classification to clustering. Many clustering algorithm depends on some pairwise distance matrix, and the choice of distance is very important. If the support is some manifold, it's reasonable to replace the Euclidean distance by its intrinsic distance called the geodesic distance. For example, in this figure, it shows the geodesic distance is a distance along the curve, not the Euclidean one. So the geodesic distance is the length of the shortest path on the manifold connecting two points. And unfortunately, it's only computable if the manifold is known and the manifold is very simple. For some cases, even the manifold is known, you cannot calculate the geodesic distance because it's too complicated. You need to solve some geodesic equation. And also, in most applications, the manifold itself is unknown. So that means we need some geodesic distance estimator. The current algorithms combine some local and global estimation. For example, in this beautiful paper where the isomap was proposed, so they estimate the distance between local neighbors by the Euclidean distance. This is not surprising because we know the manifold is locally flat. It's locally similar to a Euclidean space. And for non-neighbors, they use the so-called graph distance. Here's one figure showing how this graph distance works. So for any 2 points that are neighbors, distance is just the Euclidean distance. For 2 points that are non-neighbors, you just construct this graph. And so you connect each point with its neighbors, and the weight of each edge is the Euclidean distance. And then you search on the graph, what's the shortest path between these 2 points on the graph. And then you calculate the length of that shortest path and use that as the estimation of the geodesic distance. And in this paper and a following paper by the same author, they show that as the sample size goes to infinity, this graph Euclidean distance converts to the true geodesic distance. Okay, but without any rate. So our contribution is to replace the locally Euclidean distance by a locally spherical distance, because we have seen that the spherical distance has the spherical approximation has a better performance than linear approximation. So we show that if gamma is an unknown curve and this S is the true geodesic distance between X and Y, then the Euclidean distance is equal to the true distance plus the error term S cubed. Our spherical distance is equal to the true distance plus a better error term as to the 4. So that means locally the spherical approximation has a better error rate. Here's the 2 example, the Euler spiral, where we know the ground truth, we know the true geodesic distance. And here the X coordinate is the true distance S, and the Y coordinate is the error of the distance. So you can see that this is the Euclidean distance, which is the worst, And the blue ones, our spherical distance is the best. And in the middle is another competitor called the Coherence correction distance. This is done by a group of people at Duke Math department. So basically they're estimating the distance by the Euclidean distance plus a correction term, which depends on the coherence matrix. That's why it's called the coherence correction distance. And you can take the log to see the different rate. So the spherical distance has a better rate, and the new simulation result match our theory. So we want to use this new estimation of distance to do clustering. This k-medoid algorithm is it's very similar to k-means. It also minimizes the distance between points in each group and the group centers. But the difference is that the group centers are constrained to be some sample size, to be some sample points. But for k-means, the group centers can be any point. And the input of this k-medoid is only the pairwise distance matrix. So we have 4 choices for distance. We can either use a Euclidean, graph Euclidean, which is used in isomap, or like graph spherical. We call it K-Estimator. Estimate is spherical. You can see these 2 examples. The first panel is k-means. We all know that k-means doesn't work for this kind of data. And k-medoid and Euclidean medoid that do not work for this small sample size case, but spherical medoid works, because even for this small sample size case, we can still approximate the geodesic distance better than the Euclidean case. We have also some real data, so I guess I don't have time to talk about details. The banknote, I guess you are all familiar with this very simple data set, and here the intrinsic dimension is chosen to be 1. So we tune this by cross-validation. I can see the 6 measurements. In terms of all these 6 measurements, we have the best performance for the spherical approximation. And another real data set is a galaxy zoo. This is my favorite example. It's collected from the galaxy images. And the 2 groups are spiral galaxy and the elliptical galaxy. And here the ambient space dimension is 6, and the intrinsic dimension is only 1. And you can tell from this measurement that this data set is harder to classify or cluster than the banknote. And so basically, graph Euclidean and the global Euclidean completely fail because these 6 measurements are very small, very close to 0, but sphere is kind of work. Okay, another application is the conditional density estimation. This kernel density estimator is very popular. So this acts as some covariates in R to the P, and Y is the response. Given some covariate X, we want to estimate the conditional density of the response Y given X. And here is the kernel density estimator, where this kernel is chosen to be the Gaussian kernel, e to the negative distance square, divided by H1, where this H1 and H2 are 2 bandwidths. So then we can replace this Euclidean distance by spherical distance. And then you will get the new kernel density estimator, which we can call it a different kernel. I will talk about the new kernel in 1 minute. Here's another real data example, is the compact cycle power plant data set. And the dimension is 4, intrinsic dimension is 3. And you can check the sum of log likelihood. The worst one is Euclidean, which is not surprising. And this is a graph Euclidean used by isomap. And this is a coherence corrected distance by halting the group at Duke. And this is our graph spherical distance. So you can see the order is exactly the same order as we check the local distance approximation performance. And similarly, if you don't want this conditional density, you just want some point estimator of Y. So we can do some mean regression. That means we can take the expectation with respect to Y of the right-hand side. So you have this kernel regression or mean regression. Given X, the point estimator of Y is given by this formula. Still, there's a Gaussian kernel involving a Euclidean distance. We can replace the Euclidean distance by spherical distance. And actually, this is replacing the Gaussian kernel by the so-called remaining Gaussian kernel, which was proposed by this beautiful paper in 2017. So they want to generalize the Gaussian distribution to any remaining manifold. And the idea is very simple. So in the Gaussian distribution, you will see some norm square, and you replace the norm by the geodesic distance, you get this so-called Riemannian Gaussian distribution. But the problem is the manifold, first manifold is always unknown, and the other one is that the distance is uncomputable, even if the manifold is known. In their original paper, they have only one toy example where they can write down the geodesic distance. But in practice, it's hard to consider or hard to apply this Riemannian Gaussian. But by our spherically trick, we can approximate the geodesic distance. Then we can use the so-called Riemannian Gaussian kernel as a new kernel and replace the Gaussian kernel by the Riemannian Gaussian. Here is the regression performance, the root of mean square error. Again, you will see the same order: Euclidean the worst, graph Euclidean, coherence corrected, and our graph spherical. So it's always this order. No matter you check the distance approximation error, or you check the sum of log likelihood of the density estimation, or you check the root of mean square error from mean regression. So that's basically my talk. The take-home message is that we can use spheres for local approximation instead of planes. You can replace PCA by spherical PCA. You can replace the Gaussian kernel by Fisher Gaussian kernel or Riemannian Gaussian kernel in this mean regression setting. And you can replace the Euclidean distance by spherical distance. There are many applications. I have talked about manifold learning, density estimation, classification, geodesic distance estimation, clustering, conditional density estimation, and regression. And we can also do denoising and visualization. If you are interested in, you can find examples in our paper. And there are many future interesting works. So first, we want to generalize the spherulate to ellipsoid or quadratic surface. We have a new archive paper last week. So we generalized the spherulate to ellipsoid. Actually, it's a special kind of ellipsoid, but we will lose the closed form solution of spherulates. For this ellipsoid approximation, we need to do some gradient descent. And I guess for a general quadratic surface case, it's even harder. We also want to scale up to large P and large N case, like sparse PCA. We want to develop some sparse PCA, sparse SPCA. And we want to address some non-Euclidean data, like categorical data or functional data. Okay, that's my talk. Thank you very much.
Okay, thank you, Dr. Li, for your excellent talk. So now is a question. I saw one question in the chat list. So maybe that is Jean-Christophe. Yeah.
Oh, there was a theorem, I think it was on slide number 9. There was an alpha, and I was wondering if it was that the theorem was valid for every alpha in 0, 1, or if it was that there exists alpha in 0,
1. There exists, sorry, this alpha epsilon depends on both m and alpha, and epsilon. You have to calculate
I hadn't seen that it was written, actually. But then, how do I know that alpha is not equal to 0?
Yeah, so there's a definition of alpha epsilon. If the manifold is known, then you can calculate alpha epsilon for any epsilon. So the details is as follows. So the alpha epsilon is the volume of a submanifold divided by the volume of the entire manifold. And the submanifold depends on like the location where the principal curvature is changing in a small range. So it's computable. It's not the existing, like there exists
so for instance,
a constant, something like that.
In the case of you showed a picture of a Swiss wall, which is like in 3D, it's like a 2D surface.
Yeah.
And in this case, the Gaussian curvature is 0, so maybe it's hard to approximate by spheres. No? So in this case, do you know how alpha epsilon behaves?
Yeah, that's a very good point. So the point is Gaussian curvature is not appearing in the proof. So the quantity that affect this alpha epsilon is the change of principal curvatures. For the spherulate case, for the Euler, for the spheral case, the Gaussian curvature is 0, yes, but the principal curvatures is 1 and 0 in 2 directions or 2 perpendicular directions. So that means this alpha epsilon is not close to 1 if the alpha is very small, but still it works better than the hyperplane case. This is not surprising because we know that the principal curvature or the normal the curvature in any direction ranges from 0 to 1. And depending on the distribution of the data, maybe the best curvature representing this sphere can be any number between 0 and 1. So this sphere list can find that best curvature representing the local pieces. We can find it automatically from the radius. But if you just use a local linear method, you are assuming that the curvature is always 0. That's why we have a better performance, even if the curvature is changing rapidly. In that case, yes, the alpha epsilon is not very close to 1, but still it's at a better practical performance.
Thank you.
Okay, so any other questions? So at the beginning, I saw you assumed that the eta follows normal Gaussian distribution or something, or you always assume you have this assumption in your data or something.
You mean the noise or?
The noise, yeah.
Oh yeah, for this for this manifold learning, we don't need that assumption, but it's only required for this classifier. If you remember this asymptotic misclassification accuracy, yeah, here we assume the IID Gaussian distribution. But if it's not IID Gaussian distribution, you can still prove a similar upper bound, but it's more technical and much more complicated. So basically, you want to bound the norm of the error when you want to show this theorem. Yeah, if it's IID Gaussian, then the norm is basically chi-square IID chi-square, so it's very easy to bound it. But otherwise, it will be harder. But still, you can prove a similar upper bound here. This is a very used assumption. But otherwise, we don't need this IID Gaussian noise assumption.
Okay, so maybe I think you can change to super Gaussian something. But if you only assume finite moments, for example, maybe the results, I don't know whether you still have that bound or not, because usually it really depends on the tail probability of the noise, right?
Yes, exactly, yes. We want to bound the tail of the norm of epsilon I. Yes. Mm-hmm. Yeah, sub-Gaussian is good enough, I guess.
Okay.
Yeah, thanks.
Any other questions? Okay, there's one, let me see. This is on page 13, the toy example. I don't know how to unmute that.
Oh yeah, yes. I see the question. Yes, so yeah, so it seems that this is a uniform distribution, but actually it's not. We are generating this data from some weird distribution, and we don't even know the ground truth. But yes, in practice, the observation may not be uniform, and Fisher-Gaussian. We observe that Fisher-Gaussian works in most cases, but I guess if the density is really low in some regions, it's hard to estimate it because we don't have samples there. And so in the proof, we do need some lower bound of the density function. We need to assume the support is the entire manifold. But if there's it's a very interesting question. If there's a low density region and how to adjust these low density regions. Yeah, that's a very good question.
Okay, any more questions?
Oh, thank you.
Okay, so if there's no more questions, let's thank Dr. Li again for the wonderful talk. Thank you for attending this lecture.
Thank you.
Thank you.